Pluto is a far-off and covertly more honest planet that was once a piece of our nearby planetary framework. However, recent unsettling declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggested that this icy world is on a potential collision course with Neptune. But how could this truly happen? And what might be the consequences of such a tremendous event? Are we witnessing a dazzling cosmic whimsy? Or is there more to this approaching celestial misfortune? Join us as we examine the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the vast universe. According to recent estimates by leading experts, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising concerns about a potential catastrophic collision between these two planets, which could pose a massive threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its exceptionally elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, which is 17 degrees to the ecliptic plane. This means Pluto's path is considerably more erratic compared to other planets. This inclination and eccentricity add layers of complexity to its orbital arrangement. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the inevitable question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The examination of Pluto's orbit began shortly after its discovery. Initially, astronomers sought to understand its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and unpredictable shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit despite these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on their starting positions and how they pull on each other. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex way. Several terms are key to understanding this interaction. Non-simultaneous libration, for example, refers to the fact that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from meeting. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or another giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another key factor is the VZK wobbling, named after three scientists, Vashkov, Zeldovich, and Kaluza, who studied how objects move in space. This wobbling involves how three celestial objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This interaction influences their movement. In Pluto's case, the VZK wobbling helps explain why its orbit near the Sun is so peculiar. Despite Pluto's orbit appearing chaotic, this wobbling helps keep it moving smoothly over long periods. The VZK wobbling demonstrates that although things in space may seem wild and unpredictable, patterns and rules maintain some control. These forces help stabilize Pluto's orbit, ensuring that it doesn't collide with Neptune or veer off course. This three-body problem is crucial in understanding how these orbits change due to the gravitational pull of celestial objects. Studying this helps us learn more about Pluto, our solar system, and even distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite its stabilizing properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over centuries. However, these peculiarities in Pluto's orbit have been found to maintain stability over very long time scales. Monitoring disruptions through advanced simulations has helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps stabilize Pluto's orbit. However, Neptune isn't the only player at work. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, and Saturn contributes as well. Studies show that Jupiter's massive gravity is strong enough to keep Pluto on a steady path for a very long time, possibly even millions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These peculiarities are essential for keeping everything in place in space. Without these mechanisms, the solar system as we know it would be a much more violent place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of our nearby planetary system. The case of Pluto is a testament to the complex beauty of celestial mechanics. The intricate gravitational interplay between Pluto, Neptune, and other planets is a prime example of the delicate balance within our solar system. The synchronization between Pluto's and Neptune's orbits, known as an orbital resonance, ensures that despite their paths crossing, they remain in a stable relationship. This resonance prevents close encounters, as the timing of their orbits ensures they are never in the same place at the same time. Adding to this complexity is the role of chaotic dynamics in celestial mechanics. While Pluto's orbit may seem unpredictable over shorter timescales, long-term simulations suggest that its overall trajectory remains stable for millions of years. This stability arises from the combined effects of resonance, gravitational influences, and the vast distances separating the celestial bodies. The influence of Jupiter and Saturn on Pluto's orbit cannot be understated. As the largest planets in the solar system, their gravitational pull extends far beyond their immediate vicinity, acting as a stabilizing force for smaller bodies like Pluto. Their influence helps maintain the intricate dance of the planets, preventing catastrophic collisions or ejections from the solar system. The case of Pluto and Neptune highlights the importance of understanding orbital mechanics in predicting potential threats to Earth and other planets. While the likelihood of a direct collision between Pluto and Neptune is minimal due to their synchronized orbits, the study of such interactions offers valuable insights into the broader dynamics of the solar system. Looking beyond Pluto and Neptune, similar orbital resonances and gravitational influences exist throughout the cosmos. These patterns are critical for maintaining order in planetary systems, both within our solar system and in distant exoplanetary systems. By studying Pluto's unique orbit, scientists gain a deeper understanding of how celestial bodies interact and coexist in the vast expanse of space. In conclusion, while the idea of a collision between Pluto and Neptune might seem alarming, the precise and delicate nature of celestial mechanics ensures that such an event is highly unlikely. The gravitational ballet of the planets, guided by fundamental forces and intricate dynamics, showcases the harmony of our solar system. Pluto's story is not just one of a reclassified dwarf planet, but a testament to the incredible complexity and stability of the universe we inhabit. This text shows how even the most apparently unsteady circles can arrive at a condition of equilibrium through the complex collaboration of gravitational powers and orbital mechanics. It also highlights the significance of steady perception and investigation of these peculiarities to better comprehend our place in the universe. Exploring the depths of space often drives us to confront the unusual nature of celestial bodies. Pluto's orbit is an ideal illustration of this inconsistency. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computerized simulations has been immensely helpful for scientists in understanding how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune interact gravitationally. By tweaking small details in the simulations, space analysts can see how even minor changes can create a significant difference in where Pluto ends up. In the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Despite having features like non-synchronous libration and orbital precession to keep it stable, its orbit can still be inconsistent and surprising. A small difference in Pluto's starting position or speed could result in a completely different trajectory after just a few years. Yet, despite this apparent chaos, Pluto's orbit remains stable over immense timescales, billions of years. This implies that Pluto's journey around the Sun has an inherent order, even though it might seem wild at first. Predicting celestial movements, particularly irregular orbits like Pluto's, is a significant challenge. The inherent unpredictability of such systems means that long-term forecasts are often riddled with uncertainties. While mathematical models provide excellent tools for understanding and predicting celestial motions, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Beyond the chaotic nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we've made significant strides in understanding space, Pluto's case undoes how much remains unknown about the cosmos. Grasping the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly influence the stability and trajectory of other bodies within the system. This is why leading astrophysicists have recently raised concerns about a potential collision between Pluto and Neptune. Despite the intricate forces preventing such an event, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving understanding of celestial mechanics and the public's interest in the overlooked corners of space. His stance on Pluto's reclassification is based on the ever-expanding knowledge of our solar system. He views the reclassification not as a diminishment, but as a necessary adjustment to our growing understanding of the diverse bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The curiosity about these questions keeps the exploration of space exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the fate of Pluto's orbit suggest that we may still have many mysteries to uncover. Will Pluto collide with Neptune, or is this just another moment of chaos in the ever-changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we truly know about our own solar system. We continue to study these celestial phenomena with the goal of uncovering more secrets. The possibility of a Pluto-Neptune collision raises yet another question about the puzzling and captivating universe we inhabit. Such a collision would challenge our conventional understanding of planetary stability. The idea that two celestial bodies with vastly different characteristics could collide is both unsettling and fascinating, especially considering the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be profound. It would affect our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed primarily of nitrogen, methane, and carbon monoxide. Conversely, Neptune, a gas giant, is made mostly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would drastically affect their structure and behavior, potentially creating an event observable across vast cosmic distances. What makes this hypothetical collision particularly captivating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. Jupiter, the largest planet in the solar system, exerts a stabilizing influence on Pluto's orbit, preventing it from straying too far into Neptune's region. Additionally, Saturn's gravitational pull further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. However, despite these apparent safeguards, ongoing research has also shown that the relationship between Pluto and Neptune is not as simple as a clear collision course. The gravitational resonance between the two planets, where, for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a kind of celestial lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while crossing in the vast expanse of space, have never resulted in a collision.